where are we going? We're going to spend the next 2 weeks doing basically equations of constant acceleration type problems. And one of the reasons for this is to really spend some time right up front practicing your problem solving skills. As I said in physics, they're word problems basically. That's basically all we do. But they're very different word problems than a lot of you have been used to. And getting used to reading them is really the key skill you need in this class. And what the 2 weeks should show you, because we're only going to use 3 equations for the next 2 weeks. That's it. And we're going to do lots of different example problems, and surprise, surprise, every time we do them, we'll be using one of the same 3 equations. But they're going to be in different permutations, different combinations. You're going to start to see some of the words we use in English to describe physics situations that you need to understand that show up throughout the course. So what you want to pay attention to is not the surprising fact that I use the same 3 equations in every problem for the next 2 weeks. But is why am I setting up the problem the way I am? Why am I using the equations and the combination I'm using? How am I thinking about the problem so that I can get an answer? We're also going to do some fun demos and some other things next week just so you can see how projectile motion really works. Now, to do this, one of the first things we're actually going to do is we're going to open with a clicker question today. And the idea is the following. One of the most fundamental things we do in motion is we turn around, right? I'm walking this way. I'm going to hit the wall. So I got to turn around and walk this way. Now, if I'm going to turn around, I have a couple choices, right? At some point in my motion, I might need to have 0 velocity. Now, at some point in my motion, I might need to have 0 velocity in the original direction of motion. I could also use the word speed here because I'm talking about just the component or the part of my velocity that's in my direction of motion. So notice there's a difference between A and B. They're different. But they could both have to be true. Or neither A or B could be required. I could just turn around real quickly, right? I mean, that's something I could do. I could turn around real quickly. You know, I've started doing insanity. Can you see how it helps? Yeah, if at some point in the quarter I stop showing up, you know why. I can't walk anymore. So if you're required to turn around, just do it quickly enough. So A, B, C, or D? Excellent. Let's stop. Look where we are. An interesting spread. Now this is excellent. Because why do I say this is excellent? Almost nobody picked D. You all pretty much had the sense that something has to go to 0 for me to turn around. Now, I'm going to turn around 2 ways, and I want you to re-vote. So I'll start it. Did it start? Yes. So one way I can turn around is I can do this. Another way I can turn around is I can do this. That was very well expressed over there. So now re-vote. And if you don't know why those 2 things gave you the right answer, talk to the person next to you, see if they did. The key is the second way of turning around. By the way, those of you picking D, I already announced that was wrong. Okay, 10 more seconds. Vote real quickly. 5. That was a quick 5 seconds. 4, 3, 2, 1. We all good? Excellent. We got most of you to move to B as we should. Notice this is a key idea in physics. We have to keep in mind what I mean by velocity. Again, there is no way, and I'll show you in a second, to turn around without stopping in this direction. I have to stop in the direction I'm moving, or I can't turn around. Think of it this way, and we're going to draw a graph. I'm going from, say that's positive, a positive speed in this direction, is positive velocity in this direction, to a negative velocity in this direction. The only way to go from positive to negative is to go through 0. However, my velocity, which is what A is, does not have to go to 0 because I can be moving in a curve. As I go this way, I never have a 0 velocity. Right? I was always moving. But what happened was there's a point where I'm facing directly at you. Once I'm doing that, I'm only moving this way, so I have 0 velocity in this direction. So my velocity still went to 0 in this direction, even though it never went to 0 as a total velocity. So that is the key to this idea. And the reason it's important is this is a key component, okay, of many problems that you'll face. That this is not true, but this is true. And you will use this fact in the course of your solution. But it won't necessarily be stated in the problem that you had 0 velocity in the direction of motion. All that will be stated is you turned around. And given that English statement that you turned around, you will need to convert it to this mathematical fact. Another way to think about what we are doing today is learning the conversion of English statements to math statements. And I'm going to try and highlight that as much as I can when I solve the example problems, but it's something you want to pay close attention to at all times. When am I using some English statement? And it's particular math statements. It's math statements with a physics meaning. And that's very particular. So that's the idea we're going for. If the visual should have helped you. If you're more graphical and mathematical, we can look at it in our following plots. Right. So if I'm plotting my position as a function of time, and I consider this 0 and that positive, right? I could be moving, slowing down, slowing down, slowing down, slowing down, stopping, turning, speeding up, speeding up, speeding up, speeding up, and walking faster. What would that look like? That would look something like that. Where at this point right here at the top is where I stop and turn around. How do I know that the point at the top there is where I stopped? The slope is 0. And what's the slope? The velocity, because velocity is dx dt in this direction. Right? It's the part of the velocity in the x direction is dx dt, which is the slope. And if you notice, it's positive here, and it's negative here. That's a positive sign, actually. So if I were to plot my velocity as a function of time, well, it wasn't very good, but it does that. In this case, it's a nice straight line. And right here is where it is 0. And it's positive here, and it's negative here. Given this, what's my acceleration as a function of time? Since this is, the velocity here is a straight line. Oh, I already wrote it. Is a straight line. What's my acceleration now as a function of time? Anyone have a suggestion? Is it a straight line that's going up or down? Is it a curve, or is it a horizontal line? Horizontal line, is it positive or negative?
Negative.
Negative, because the slope is negative. What does this mean? And this is where, so the acceleration is less than 0. Again, it's the derivative of the velocity. So it's the slope of that line. Let's think about this physically, right? I said that direction's positive. And this is where acceleration, the plus or minus sign for acceleration, is one of the most confusing things. So you're going to want to watch for it in the problems. But I'm slowing down in the positive direction. So that's a negative acceleration, because my velocity is getting smaller and smaller. Notice when I turn around and I speed up in the negative direction, my acceleration is also negative. So it was negative slowing down in the positive direction, and it was negative speeding up in the negative direction. So if I divide this into two regions, it's negative when I was slowing in a positive direction, and it was also negative when I was speeding up in a negative direction. Now, if you're very careful and you draw the right pictures and you pay attention to derivatives a little bit and slopes, you will always get the minus sign right. But it helps to have a physical intuition that the minus sign for acceleration, the direction of your acceleration, is not as intuitive as the direction of your velocity. The direction of your velocity is which direction you're moving, right? This was moving forward, and this was moving backward. Notice the minus sign of your position is just where you are, right? At all points, since I called this 0, I was always at a positive position. Even when I was moving that way, I was still at a positive position. So you really got to keep track. For each of these three things, the minus sign means something different. And the best way to see it is to see it in all the problems we'll be doing. Any questions on that? So let's ask ourselves, what are, I said we're going to be using 3 equations. Basically, we're going to take our definitions. So we have velocity as a function of time is the integral of acceleration over dt. But we're going to be focusing on, I didn't give myself enough room, constant acceleration. So I will be doing the integral of a being a constant dt. What's the integral of a constant?
0.
Oh, you just got it backwards. That was very confident, though. I like it. The derivative of a constant is 0. What's the integral of a constant? Linear. It's a times t, plus we have to add some arbitrary constant when we integrate. We're going to call that v naught. Why do we call that v naught? Because if I plug in t equals 0, I have v has to be whatever velocity is at t equals 0, which we call v naught. So that's our first equation of constant acceleration. Our second one, we now get from integrating the velocity to give us the position. And what is the integral of a constant times time dt? Okay, it's t squared, and what else do I need in front of it? My 1/2. So when I take the derivative, the 2 cancels the 1/2. Again, the nice thing, and I get my v naught t because that was a constant, and I have to add my x naught. I don't do many derivations in this class, but this is one set of equations we use a lot. You'll probably just memorize it by using it a lot. But you might say, for instance, forget the 1/2. If you remember, this comes from integrals and derivatives. When you see the t squared, you know you're going to need the 1/2 because that's what goes with the t squared. So it will help you remember it. Now, what we like to do is take this and subtract our x naught, because what is the final minus the initial position? What did we call that? The change in x, and we called that the displacement. So we can write it as a single equation for the displacement, and we like to put the t term first and the acceleration term second. That's it. That's just our two equations. And let's rewrite them just for fun. And I want you to notice something. What do you notice about the right-hand side of this equation? How would you describe that? As what? How many terms are on the right-hand side? 2. And what are they? And I'll give you a hint. Are they vectors or scalars? Vectors. So both of these equations are a vector A equal to the sum of two other vectors B and C. So these are vector addition, which, as you will see, we're going to do 1 D1s this week and 2 D1s next week. You can either add head to tail graphically and draw them, or you can use components. But they're fundamentally the simplest type of vector addition. Because it's just two vectors always being added to equal a third, it will always be a triangle. And triangles are nice and easy to use. Now, there is a third equation that is very handy. It actually comes from these two if we eliminate time. And we write it as v final squared equals v naught squared plus 2a dot delta x. And this dot here is important. We're going to use this in a number of different places. It will tell us the minus sign for this term. And to start with, if A is the same direction as delta x, then it's positive. If it's opposite, then it's negative. And that's all we have to worry about for now, for this week. As we move on, we're going to do dot products, and you'll see that there's a cosine theta there that we have to worry about. But that comes in later when we do work. This is just a warm-up for it. In reality, you could do every problem with just these two, but this third equation makes life a lot easier. Any questions on our 3 equations? There's a lot more in the book. Physics books like to give you a whole bunch of other equations associated with constant acceleration. I strongly recommend ignoring them. This is pretty much everything that you're going to need. And to go with that, you want to be able to draw your pictures. So remember, in 1D, this is the vector A, and then all you have to remember is that that's the vector minus A, the opposite of it. So it's pretty easy to draw things. If I have a v naught t, and I have a 1/2 at squared in the same direction, then that whole thing is delta x. And notice, the key piece here is the head to tail. This was where v naught was positive and a was positive, if that's the positive direction. If I have some v naught t, but a is opposite v naught, then 1/2 at squared looks like that. And that's my delta x. And once again, there's my head to tail. And those are the kind of pictures I'll be drawing. Yes?
In the previous equation, the displacement vector, is that supposed to be the actual equation for displacement, or is that
This is
no, on the bottom.
right here?
No,
Here?
No, the last equation.
This. This is the displacement vector, delta x.
So that's an actual value, not an equation.
Yes.
Okay.
At whatever time you're considering your final time where you want to find that velocity. So it is, for instance, in this picture, it would be this vector here, delta x. Notice, we're a little sloppy with notation. This really is delta x of t because it's for whatever time t those are. I have assumed a particular time t by drawing these vectors. Any other questions before we start our example problems? So mostly what's going to happen now, there'll be a brief interlude where I look at vectors in 2 dimensions sometime in the next 2 weeks. But most of what's going to happen now will be in the context of either example questions or demos. I would like to do this little quick clicker question before we go into the problem. Because we have to pick our coordinate system, right? I've constantly been picking plus and minus. We'll have to pick x and y when we go 2 dimensions. So as we enter our problems, think about this. When you pick a coordinate system, you can use different ones for position, velocity, and acceleration. Velocity and acceleration need to have the same coordinate system. Position and velocity need to have the same, or they all need to be the same. Okay, most people went with D. So let's look at my answer, and indeed D. You have to be really careful with this. It is one coordinate system for the whole problem. Because, remember, velocity is the derivative of position, acceleration is the derivative of velocity. They only make sense with the same coordinate system. Another way to think about it is we wrote it down as a vector addition equation. So if you go back to that, drawing these pictures would not make sense without the same coordinate system. So you have to do that. Now you might use a different coordinate system for 2 completely different motions in the problem that are not related. But that's a different issue than using it for the position, velocity, and acceleration. So let's go to our first example. Hopefully you noticed it was printed out. We are putting at our miniature golf course. Fun thing to do. And this is a special one. You actually have to get the ball to stop exactly 15 meters away from where you hit it. Otherwise, it doesn't work. Don't ask me how that is, but that's just the way it's designed. The ball has a constant acceleration of 2 meters per second squared in magnitude, and it's slowing down. How fast must you hit it to get it to work on the first shot, meaning you get it to stop right there? Notice, we want to look for our key words here. One of our key words is that the ball stop exactly 15 meters away. Whenever you see just stop, stop exactly, stop, 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 what does stop mean? That's going to be something we're going to want to focus on. We are noticing the question, how fast must you hit it? So we're immediately looking for some velocity. We are told that the ball is slowing. So if it's slowing down, we know the acceleration is opposite the velocity. Otherwise, it wouldn't slow down. That's what slowing means. These are some of our key words. We actually have a clicker question, though. This is the first time we've seen the idea of stopping or just stopping. So, what does it mean for the ball to stop or just stop? The speed is 0, the acceleration is 0, both A and B, either A or B. We're not doing very well of convincing anyone of anything here, unless you all just flipped. We're still looking at 50-50. We flipped a little bit. You can keep voting. I haven't turned it off. I'm just showing the graph. You might be influenced by those around you. Okay, everybody clicked in? 5 more seconds. 4, 3, 2, 1. So we moved heavily towards just the speed, not the acceleration, which is correct. Now, someone tell me, what word in English might I use if I want both the acceleration, what phrase? If I want both the acceleration and speed to be 0. What phrase might I use that would convey that information? You're not allowed to use any words like velocity or acceleration. You have to use other English words.
Complete stop?
Nope. But I think I know where you're going.
Staying still.
Stops and stays still. Stops and doesn't move anymore. Complete stop still kind of implies just going to 0. Might imply not moving again, might not, depending how you think about it. The clearest thing is to say it stops and doesn't move. Or it stops and stays still. That would be acceleration 0 as well, because you've created a velocity that's not changing anymore. In this case, all I need is for it to just stop. So that's the key piece. We're just getting it to stop. So now I'm actually going to go and work through it, and I'm going to do it in 2 ways, as we have often done. And the first thing I'm going to do is probably I'll just sketch a picture for myself, right? I have the ball going here, and it has to go here to some point 15 meters away. I know the acceleration is in that direction, and it's 2 meters per second squared because it's slowing down. On the off chance that I use components, I'll always pick my coordinate system. This time I'll pick the direction it's moving. I know that here I hit it with some speed. I don't know what it is. I'll call that V0. And at V final, I know it stops, so it's 0 meters per second. That's the sort of thing you'll want to very quickly do in your situation and variable. When in doubt, just get it down as a picture so you really know what all the pieces are. Now, having done that, I can immediately draw what I call my vector diagrams. Right? I know delta x is going to be equal to v naught t. Well, oops. Let me do it in the other order, actually. I know I've got v naught t plus 1/2 at squared, and this is, notice, opposite v naught, and that's going to equal delta x. Notice in this equation, right, as an equation, I can now write this out. This is the one I have up here. And I can immediately see that this I don't know, and this I don't know. Delta x I know, and a I know. So I would need, if I'm going to do it this way, I would need another equation. I'm told I have 2. So my other one is that I stop. So I know that v naught plus at, whoops, has to look like this, because it would equal v final, but v final equals 0, so it has no length. And so I know v naught equals at. Notice this did not introduce any new unknowns, right? I don't know this, I don't know that, but I know that. So I have the same 2 unknowns. I now have 2 equations. I could do the problem. Any questions on that? It's showing a couple of things. I'm highlighting, on the one hand, correctly drawing A in the opposite direction of V when it is opposite. On the other hand, I'm also highlighting what happens when one of your vectors is 0. The two end up equal to each other. The third thing I'm doing is with this equation right here. Once I've drawn it like this, I can, without worrying about the minus sign, see that this is delta x plus 1/2 at squared, where everything is now a positive number, because I'm just adding these line segments up, has to equal v naught t. So this equation and this equation will be the two I use, where now every number is a positive number and I don't have to worry about minus signs. Those are the three things you want to make sure you understand when you go back and look at this problem. Why this becomes positive signs, why the a's are backwards, and why that's a 0. Any questions on those three things? Again, it may not make immediate sense right now, but as you go back and look at it, work over it, do the homework problems, this will make a lot more sense. Now, when I put those two equations together, just real quickly for you, I have v naught equals at, so I can plug that into my delta x equation, right, which was v naught t equals delta x plus 1/2 at squared. So if I plug that into there, I have at squared equals delta x plus 1/2 at squared. Do you see that? I took my at and plugged it in for my v naught. Now I can solve for t squared, and I'm going to skip a little bit of algebra here. Notice what I'm doing. I like to do everything in my variables and plug in my numbers at the end. If you're not comfortable with that, you can plug in numbers as you go along. But I find this much easier to keep track of stuff. That's just me. Now that I've got t, remember my original question was what's v naught? I can come back and plug it in now. And if I do that, I will get v naught equals the square root of 2a delta x, which equals 8.7 meters per second. Anyone tell me, what does that look like? I know it was just quick. We had another equation. Does that look like part of it? Anyone remember seeing an a delta x anywhere? Or even better, a 2a delta x? We had this. So this is just to prove another point I made earlier here. You can do everything with these two equations, but remembering this one will really help save you time. And it'll help save you time when time isn't mentioned in the problem. Okay, yeah. I told you, we're videotaping you and grading the laughter. So in this particular case, right, what I noticed is that I'm going to be stopped. So that's telling me v final is 0. And I want v naught, given a is 2.5? Yeah, I think 2.5 meters per second squared, and delta x is 15 meters. You want to get used to noticing that sort of situation, where you're given stuff about delta x and a, or you're given v final, v naught, and one of those two, and you want to find the other, because now I can do it in kind of one step using this equation. I have to get this minus sign correct. So it still helps to have my picture. Notice delta x is that way, a is that way. So are they opposite or in the same direction? They're opposite, so I have to remember, since a is opposite delta x, that implies I get a minus sign. Notice, physically this should make perfect sense to you, right? If a is opposite delta x, then I'm slowing down, and v final has to be less than v naught. The only way that can happen is if I put a minus sign here. Okay? So now I plug in, I have 0 equals v naught squared minus 2a dot times delta x. And I can get rid of my vectors because I made it negative. And so now I know v naught equals the square root of 2a delta x, which if you look up here is exactly what I had. So notice algebra-wise, much quicker. Much quicker. But you have to be used to recognizing that as a way to solve the problem. Any questions on this example? Yes?
Go up to the first.
Sure.
That one. Which equation would you use? Because you put two different ones.
I am using two equations right here.
No. Go from that same one.
Right here?
That
Yeah.
one and the one that run right below it.
So what I'm doing, that's a very good, you know what, let me redo it here real quickly, okay? My main equation is this. And I'm going to use this to either do one of two things. Write it as components. In this case, if I made it positive to the right, that's 15 meters. This is some unknown velocity times t. And this is to the left, so it's a negative 1/2 a t squared. And a is the 2.5 meters per second squared. That's if I was going right to algebra. I will also use this to draw my pictures. I know that it's v naught t, that's this vector, plus this vector, but this vector was going in the opposite direction, so it's some 1/2 at squared. And these two together equal the third vector, delta x. Now, and the way I drew it up in the last slide, I admit it was a little confusing, so it's worth looking at real quickly here. Once I've drawn this picture, I can immediately just now use the lengths of lines and write down everything as a magnitude with some length. And what do I have? I have this line plus this line has to equal that big line. And so I can write delta x plus 1/2 at squared equals v naught t. And if you notice, that's the same as this with the minus signs in it. So everything was this equation. I just did it in a bunch of different ways. Now, in this problem, I have to admit, this looks like massive overkill. But it is a good place to see how drawing these pictures work. So when you get some of the more complicated problems, these pictures can help you sort of sort out what's going on and make it a lot easier. Did that answer the question? Other questions? Yes?
How did you draw the second diagram of v naught equal the same length as v?
Because I knew v final equals 0 equals v naught plus at. So when I add these two together, I have to get 0. And the 0 vector is the vector with no length. And this was, remember, that we knew it stopped. So the only possibility is v naught this way and at that way, the same length, to get 0 there. Other questions? Okay, if we look at the next problem we're going to do, what I'm just going to do now is sketch it out, and we'll work it out real quickly on Wednesday. There's a number of interesting pieces to this one. We now have two objects, a car and a police car. They have their own sort of speeds, and we have to notice what's going on. The car is going at a constant speed. There's two questions we're going to ask, one where the police car has constant acceleration, and one where it has a maximum speed. And what we're going to be doing is we're going to be looking for when they catch the police car catches the car. So that is going to be the key physics we have to understand. That'll allow us to set up some relationship between the displacement of the car and the displacement of the police car. For each of these, they will have their own equation. The car is not accelerating, so the 1/2 at squared will be gone. The police car initially is starting at rest and just accelerating. So it'll just have 1/2 at squared because v police is 0 initially. And what we'll see is in the second case, things get more complicated because the police car will have two motions, one where it accelerates, and then when it reaches its maximum speed, it goes at constant velocity. So the idea, the thing to notice here is, again, we will do this entire problem only using 2 of our 3 equations. But we're going to use them a lot. We're going to have to draw a picture carefully. That trivial picture we drew for the first problem that didn't seem to help things and was only confusing is going to become key in this problem to match everything up, to get all our minus signs right, to get all our times correct. What I would really encourage you to do, I'm going to go through this pretty quickly at the beginning of Wednesday and then do an even harder problem next. So I encourage you to look at this between now and Wednesday and see if you can solve it before you come into class.